So yeah, I'm Andrew. I'm a machine learning engineer at MD Anderson. First, I want to say I think the organizers did a great job because I can see after the panel why I'm coming next, and you'll see why too. And also, I like conferences, especially local. I'm primarily remote, and I see a lot of people that I usually don't interact with. You know, I just see their avatar or whatever through Teams, and it's funny seeing them all in person. So before I read stuff on this slide, let me just talk about this use case in general and the approach we took. Overall, you're not going to see really sexy methods or anything like that. We're just applying LLMs to medical text. But the application is really simple and also really powerful. And the more I progress in my career, I've been doing machine learning in the industry for almost 9 years now, the more I like simple solutions. And this is really one of those simple solutions that has a high impact. So when I originally put "to err is" on this slide, I thought like "to err is human." That's like the original quote by Alexander Pope, and he stole that quote from someone else. I think it was in some movie in like 2004 with Snoop Dogg in it, then he said it. But I think as this conference has gone on, not "to err is only human." AI makes mistakes too. Everything makes mistakes, and you could argue that AI is made by humans, so humans are the ones making the mistakes, but the semantic points. But to get some definitions out of the way, we're mainly focused on a couple of kinds of errors in healthcare. Diagnostic error events, there's a definition there, basically failure to communicate diagnosis or make the right diagnosis. And an adverse event is really like a harm that comes to a patient through some other kind of error. Through literature, we know that diagnostic error events, or I'm going to call them DEVs from now on, may account for 6 to 17% of adverse events. So, meaning that adverse events, they could have all sorts of causes, but a small fraction of them, really a non-negligible amount of them are from DEVs. So DEVs are really important because DEVs affect a lot of people. Specifically, I've got a quote for Americans, but it affects people all over the world. About 800,000 Americans suffer serious harms from DEVs annually. So since DEVs are bound to occur, we might as well track them in some way and try to learn from them. That's typically what hospital systems do is they've got some patient safety team that reviews safety events, see if they're associated with an adverse event, and see if there is a diagnostic error event that caused it. So really a lot of events that we're trying to categorize, we're specifically focused on capturing diagnostic error events because they really help shape standard operating procedures. So this is like a day in the life of a diagnostic error event. Starting from, I just follow the direction of the arrows. A patient has a second biopsy, some kind of healthcare event occurs and is reported. A provider or clinician may notice something in the clinical notes or the report and realize that there was a diagnostic error or there was some kind of misdiagnosis, and the report is like a safety event. And then the clinical patient safety team will take that data eventually and review it to see if any harm actually came to the patient or if there is any potential for harm that came to the patient. And then eventually some committee will review it and determine if there's any potential of improving the standard operating procedures associated with that event. So this is nice. This generally works okay, but as literature shows and as we know from experience, this kind of voluntary reporting workflow typically results in underreporting. There's a negative connotation associated with reporting errors in healthcare. You don't want to admit you made a mistake, or you don't really want to rat out a coworker if you consider it ratting out. And then on top of that, we know from data at MD Anderson specifically that of all of these safety events reported, only 0.26% of them are diagnostic error events. So on this previous slide, I showed that it's between 6 or 17% typically. So we know that there is a potential for an underreporting gap of 12%. We don't know for sure if that's the case, but that's kind of what this work is trying to find out, is if there is kind of if that gap is real or if we're really just that good. So that's kind of where LLMs come in handy. LLMs, without going too deep in what an LLM is, black box, you put text in, you get pretty reasonable text out, okay? And they've been shown to be exceptionally well-performing at like general tasks that they weren't necessarily explicitly trained on. And so we're wondering, can we leverage an LLM to instead capture DEVs, replace that second block of a clinician or provider, manually observing some kind of error occurred and reporting it, because of that negative connotation. And also, it's just an extra step they have to do. you all are, or potentially most of you are providers or clinicians. You all have busy days and already have a million things to do as part of your schedule. So anything we can do to kind of circumvent one complexity in your workflow, is a benefit to you. So the biggest part and pretty much the bulk of the work in constructing this workflow to augment it with an LLM is verifying the LLM and developing the prompts for it. And developing prompts isn't really a complex task. People call it like prompt engineering and stuff. I've seen all sorts of applications of machine learning, done stuff from like deep reinforcement learning to automatic control systems. It's, in comparison to that, prompt engineering is very simple and isn't really that complex. But aggregating the data and labeling it, that is tough. And so big round of applause to Rodney. He's our clinical patient safety specialist that had to go and sift through 300 some reports, basically label them for us so that we can actually curate some prompts and evaluate this LLM as part of this workflow. And so he actually provided us a filtering method too to aggregate these reports. Devs have a very low occurrence rate naturally, and at MD Anderson we process millions of clinical notes or medical notes per day. So if we wanted to capture devs, we would basically have to read hundreds of thousands of reports to capture enough devs to build our data set to develop our LLM to evaluate the workflow. Instead, Ronnie, in coordination with some clinicians, realized that there are specific subsets of reports that are more likely to have devs in them. Not exactly that they don't always have devs in them, but they're more likely to. And so we applied that filtering to our data set to then have a smaller subset that Rodney can go and hand label. And so those subsets were amendments in pathology reports and addendums in radiology reports. And then we also had some clinical reports, free text that like a nurse or provider might enter as part of a summary of a visit. And that's just to kind of diversify the data set a little bit. And so you can see that as part of this data set, the gross majority of it is from radiology reports, but they also have a majority of non-devs within them. And that's just to point out that most of the devs and the pre-filtering that we did were present in the pathology reports. And this is just to highlight again, this is all convenience sampling because it's just very difficult to capture a data set containing devs. So we use GPT-4. We have an Azure instance of GPT-4 that allows us to securely process data. This is what the workflow looks like. It's kind of like a chain of thought-like workflow where you take some really general prompt and then get some result out of it, feed that into the next prompt, get some result out of it, and keep getting more specific with your prompts to fine-tune the answer and get basically lead the LLM into getting the correct result that you want. So I'm going to show the prompts for each of these, but they're not really there for you to read. They're just for documentation purposes. I did highlight some key points. What context that was really kind of important to achieving the performance that we did, saying that you are a specialist at MD Anderson, that external context that the LLM was trained on, understanding what MD Anderson did seem to boost the performance a little bit, and saying exactly what they're supposed to do, summarize the note, basically just reduce the information we're going to process later in the pipeline. Again, saying, you're a safety specialist at MD Anderson, and eventually, saying provide your reasoning determination regarding whether or not there's a diagnostic error event within this note. And then there's stuff in the middle I'm not highlighting, but that's stuff that Rodney helped us figure out that specifically improved diagnostic error event detection for diagnostic imaging or radiology reports. That ended up giving us like a 10% boost in our post-processing. And then classify, this is really simple prompt. Basically output a Boolean, tell us whether or not it's a dev. Basically just summarize in one word what Analyze was already doing for us. So these are example outputs. Original report, far left, summarization and analysis on the far right. Main point being there's some stuff, a lot of stuff going in that's being summarized down to a smaller snippet, and then eventually the LLM is telling us exactly what we care about. So overall performance metrics, we achieved a pretty good recall rate and precision rate, 80% recall, 70% precision. Recall being we were able to capture 80% of the devs within our data set, and we were able to accurately predict those at a 70% rate. The nice thing about this use case too is that diagnostic error event detection is actually extremely subjective. If you ask one clinician whether or not something is a diagnostic error event, They might say something completely different than another clinician, depending on their expertise and their background. So even though the performance isn't necessarily perfect, some feedback we've gotten from stakeholders is that this is still good for them because it at least provides a consistent result in identifying whether or not a dev exists. So this is kind of a low-risk use case from an AI perspective that still can help the workflow of improving standard operating procedures. And that's why I like this use case so much. So summary and next steps. We demonstrated that LLMs can detect devs within free medical text with reasonable accuracy. We had convenience sampling. So stuff we'd like to kind of repeat the study with is with larger sample sizes. We're actually going to continue this study as part of a silent trial-esque, where we're going to try to apply this workflow towards more clinical notes and radiology reports and pathology reports to see if we can replicate it on unseen data, which we already did with our test set within our cohort, but we'd like to do it across a larger swath of medical notes that aren't as likely to have devs within them to see how well it's actually able to capture those diagnostic error events. That's pretty much it. Happy to take questions.
All right, we have time for questions. Before we begin with questions, I'd like to page the next speaker, Peichi Su. Are you in the room? Oh, there he is. Good. Okay. Question?
So. I'm curious if there were any specific characteristics of the hard to characterize cases. You said that if there was 80% accuracy, was there something special about the 20%?
They were certainly confusing cases. Like when we went back and looked to try to prompt tune a little bit, we tried a bunch of stuff, but not all of it worked very well. And the data set that we curated was naturally difficult to classify because they are addendums and amendments. So they already have characteristics that are very similar to what a diagnostic error event might already have in them. So it was already really difficult to begin with. And that's why we're still pretty optimistic about our results, is that the data set itself is very difficult.
So at what point in the diagnostic process did you use this tool? In the sense that diagnosis is often not a single point in time thing, but it evolves over time.
Right.
There's an initial diagnosis and then this. So the reports that you used, the clinical data that you used, at what point in time was that?
I'm not exactly sure at what point in time we actually retrieve the data. And we've got a data platform that all of these clinical notes and free text is aggregated within at I'm sure a weekly or daily basis or something. But the gist of it is whenever a pathology report gets documented and logged, it gets written to a database, and from that we can aggregate it and do some processing on it. It kind of really dodges your question, but just as I don't really know, but it's within a week time frame we're able to do some processing on it.
Okay.
Oh, there are a couple of questions over there. I think the gentleman in the back.
Oh, wait.
Feel free to shout.
No, don't.
Yeah.
Can you say more about what would be in the clinical notes that would be evidence of a diagnostic error? I think I follow why they might be in the addendums, but those 40-something notes with, maybe it's not surprising that there's only 3 with a clear evidence of that, because it's in my work it's hard to tell from just one note sometimes.
Yeah.
So what in those 3 notes is evidence?
From there's only n equals 3 there, so it's really hard to generalize it across a huge swath of clinical reports. But the ones that we did see, they're basically just summaries of, there was an amendment or addendum in another report, and the primary provider was actually just capturing it in a summary of their clinical report. And the neat thing about that is that the amendment or addendum might not have been documented properly or logged correctly in the database, and the clinical report was still able to catch that. The whole Swiss cheese model thing of catching diagnostic error events worked out in that case.
Notes making reference to other.
Yeah, pretty much.
Yeah, thanks. That's useful. Thanks.
Okay, thank you very much again, Andrew.
Thanks.